Guys, this video is all about isotopes and isotope notation. First of all, an isotope is nothing more than an atom of an element that has a different number of neutrons in the nucleus. If you'll recall, what defines an element is just the number of protons that it has. As you can see here, we have three examples of lithium atoms. Because it's lithium, by definition, it has to have three protons in the nucleus. That's why we have the number 3 the same for all, and you can see that there are indeed 3 blue protons represented here. The thing that can be different is the neutrons, and if you take a look at the first illustration, there are 3 neutrons there, 4 in the second and then 5 in the third. One way that we can actually write out the isotopes is just write the element's name followed by a hyphen in the mass. So an isotope of lithium that has a mass of 6 would be lithium 6, lithium 7 for 7, and 8 for 8. An alternate notation is this right here. It's where you write the symbol, and then to the left we show the mass at the top and then the atomic number at the bottom. Any charge that you'd have if this was an ion, if it was positively or negatively charged, would just show up to the top right. So let's go ahead and take a look at some example problems here. I've got several of them. We're going to focus on the 4 highlighted ones. In the first problem, they give us beryllium 9. Okay, so we know that this element is beryllium because it's in the name, so we can go ahead and just call this beryllium. We need to know the number of protons. Well, on a periodic table, this number at the top right here is the atomic number, which is equal to the number of protons that you have in the nucleus. So all beryllium atoms, regardless of the mass and how many neutrons are there, all beryllium atoms have 4 protons. And most of the time, unless you have one of these little charges there, your electrons are the same as your protons because the electrons are negative and the protons are positive, and the negatives attract each other. Okay. Don't know neutrons yet. We need to know our mass before we can determine that. So we have a mass given to us. If you remember, one of the 2 forms of notations is the hyphen with the mass. That 9 is the mass. So now it's just a matter of subtracting our protons from our mass to determine our neutrons. 9 minus 4 will give us 5 neutrons. Second one is copper, and we have no other information given to us, so we're going to find out the protons and the mass from the periodic table. So we locate copper. It is Cu. We see that it has a mass of 63.55. That's just an average of all the different isotopes. So we round up to 64 here. When a mass is not given, when they don't tell us that it's a specific isotope, we assume that it's the most common. So we just round from 63.55 to the nearest whole number. In this case, our mass will be 64. And our protons are always the atomic number. So it's always 29 for copper. So we can go ahead and write for copper, our protons are 29, and our mass is going to be 55. Okay. Let's see. Yep. Actually, it is going to be 29 and 64. That's what it was, 64. Okay, so we have, there we are. So we need to figure our electrons out. Well, remember, our electrons and our protons are going to be the same. And then to figure out our neutrons, just our mass minus our protons. So 64 minus 29 will give you 35 neutrons. And then the symbol, this time let's do the other notation. So Cu for copper, our mass is going to go at the top, 64, over our atomic number at the bottom, 29. This is not an ion, there's no charge anywhere, so we don't have anything to the top right. Next one, we have krypton, and it tells us it's krypton 81. Okay, so we can go ahead and we know this is krypton. That 81 right there, that tells us the mass. Now if we find krypton right here, you say, well, it says 83.8. Isn't the mass 84? That's just the average of all the masses that are there. This particular krypton has a mass of 81, so we always go with the mass that's presented to you. If it says it's 81, it's 81. Krypton has an atomic number of 36, so 36 protons. It's a neutral atom, no ion charge anywhere, so 36 electrons. And to determine the neutrons, it's our mass minus our protons. 81 minus 36 is 45. For this one right here, we have Mn. That's going to be manganese, so we need to find manganese on the periodic table. Manganese has 25 protons. Now, this time, there is a charge here. This charge tells us that there's a difference in the number of electrons that this atom has. Okay. So, if we think of it like this, there are 25 positive charges in this atom. We know that because the protons are positive and there has to be 25 in order to be manganese. But the overall atom has an imbalance in favor of the positive. In other words, there are 6 more pluses than there are minuses. So we can't change the number of protons, so we have to change the number of electrons. What number of minuses, when balanced against 25 positives, would give us 6 extra pluses? Okay. Well, if we have 19 minuses, if we work this out, you'd get 6 plus. So we know that there have to be 19 electrons here. That's how we got 6 extra positives. Okay. And the rest of it works like normal. We see our mass. We go ahead and take that off the periodic table because it doesn't tell us that it's a special isotope. Mass here is 83 point, I'm sorry, which one are we looking at? This one is manganese. Manganese is 54.94, so that's going to be 55. And in order to determine the neutrons, it is our mass minus our protons. Be careful. You don't want to take your electrons. In a lot of cases, your electrons are the same. But if I did my mass minus my electrons for this one, I'd get an incorrect number of neutrons because it's the protons that are in the nucleus. So 55 things in the nucleus minus 25 that are protons are going to give me 30 things in the nucleus that are going to be neutrons.